maybe that's, well, it's new, it's different, but I think it's sustainable. Thank you though for the Ravenholt series for having me. Thank you for Washington State for having me here today. So yes, we're going to talk about the winery. There is a little bit, tiny bit about viticulture I mentioned at the very end, but it's very shiny. I think you saw in the original program online, it talked about energy. I'm actually talking, there will be a small part about energy, but this is going to be largely around water. So let's talk about sustainable cleaning chemistry. First off, what to expect is we're going to look at considerations around cleaning chemistries. What would you want in a sustainable cleaning chemistry? Current practices in the winery and their shortcomings. There's a fair amount of those. Then we're going to look at this alternative potassium-based cleaning chemistry. Thomas mentioned Roger. This was a concept that Roger's now brought to life. And then finally, I'll give you some last thoughts. So let's talk about, first off, the considerations around what we would want with a sustainable cleaning chemistry. I come from the school that you do a base rinse first in a wine tank. And by the way, this is around wine tank cleaning. I come from the school that you do a base first. You really need to melt off those tartrates that are off the side of your tank. So you're going to use a base first. Probably going to do a water rinse. Then you're going to do an acid wash. And then finally a final water rinse. Now, what we need to know is we need to have considerations for the base, the acid, and then whether or not we're going to add a disinfectant. And I'll talk about it at the very end. So here's some of the considerations. First off, and I hope you all know this, and this is in the vineyard as well, it's all about safety, safety, safety. You don't want to expose your people or you to any cleaning chemistry that could hurt them. Additionally, you'd like not to hurt the environment. We've heard about that all day long, and I totally buy into all of it. And actually, in the last presentation, I saw something about reducing sodium. You saw that I was going to talk about potassium. So we're going to try to get sodium out of our cleaning chemistries. And then other things, persistent chemicals that last forever. We don't last for an incredibly long time. They're great at killing, but do we really want them around? Then we're going to go into wastewater treatment. The first off is pH. I don't know if you've ever seen this, but you can kill a pond, a wastewater pond at a winery. You know, most of those ponds actually are, at least the ones we have, are aerobic digesters. They have microbes in it. They actually have nematodes sometimes in the bottom of it as well. If you send a slug of lees at low pH wine or lees down to those ponds, you can kill the pond. And that pond starts to smell. Those nematodes die and it really smells. So you don't want to kill a pond. It also takes a lot of work to build that back up. You got to get that pH back up around neutral again, and then also get those microbes in there. Anyhow, pond management has got a whole life of its own, but we need to consider what we're throwing down the drain so that we can manage that pond better. Pond digestion. Do you really want to send down a cleaning chemistry that the pond has to digest? We'll talk more there. And then finally, if I do have to digest it, that's actually, I don't know if you can see it. Yep, there you go. That right there, those are little, I'm just my diagram of an aerator. There's a lot of energy in those aerators to keep that pond with a DO above about 1.0 in the first foot or so, which is a legal requirement. Then the other part in the considerations is water. Water is huge in cleaning chemistry. I'd like to get that back. I'd like to get water back. I also like to get some of that cleaning chemistry back as well. Why do a one shot and throw it away? And then finally, it's all good and well to say, hey, I've got this wonderful cleaning chemistry, the sustainable cleaning chemistry, but it better clean. So what's its effectiveness? But let's talk about just briefly some of the current practices and their shortcomings. First off, right away, we use usually in our acid washing, we use an organic acid. That would be citric acid is very common in our industry. It's been around, well, as long as I've been in the industry. I've been using citric acid. If I use that citric acid, I then throw it down the drain, and that's a food source for my pond. I've got a food source for my pond. I have to keep the microbes happy. You have to use a lot more electricity. I have to put more air into that pond. Why am I throwing down something that the pond has to digest? And plus, I paid good money for that citric acid. So why am I throwing it down the drain? Is there another source that we don't have to digest as well? Paracetics in the same boat. By the way, paracetic is in equilibrium with acetic acid and hydrogen peroxide. If you didn't know that, it's not a standalone entity. It's in combination with acetic and their equilibrium with acetic and hydrogen peroxide. Both of those add COD, carbon carbon oxygen demand and biological oxygen demand. More air in my ponds that I then have to turn on the aerators to digest. So let's see if there's something else we can get instead of that. Then there's various ions and gases. We mentioned sodium already today. Let's not do that because you don't want to put that sodium in your soil later on. Phosphate, hopefully all know that phosphate's not good for our water streams. You get algae blooms, nitrogen as well. You get algae blooms that then chokes out your streams and any air go in your streams for other organisms to live in, such as fish. So let's not use those if we can. Chlorine, I hope we're all in the wine industry. Chlorine's not the way to go. We know that's a precursor to TCA or leads to a precursor for TCA. Chlorine dioxide, if you don't think it leads to a precursor of TCA, see Dr. Tom Collins. Go see him right away. These are gases, by the way. You know, I don't want my people to breathe these. It would be more PPE. And now you have ozone as well, fits in that one. And then lastly, steam. You know, there is a steam cleaning device up at the winery. Sorry, I'm looking at Maddie here, the winemakers here. And that's great at that small scale. If you can go along and contain that steam and keep it safe, because you don't want people to get burned by it. If you can keep it safe in a small area, and especially for a research winery, you want to sterilize, great. But I'm using, you know, I'm at 6,000, 8,000 gallon tanks. We're talking a lot of steam. We're talking about, can I actually keep my people safe? And then on top of that, that is a lot of energy. So from a sustainability point of view, maybe not the way to go for the scale that I'm at. By the way, I like this, that, you know, AI is great. AI generates a lot of neat things. And that happened to be one thing. It's got some DNA bases there, which actually we'll talk about ATP a little later. But okay, now we get into the heart of the talk, which is around alternative-based cleaning chemistries. And this is, again, a concept by, well, you'll see here. It's actually a concept by Dr. Roger Bolton. He presented, I think it was in 2014, he presented at ACS, American Chemical Society. He presented just this last month. I presented, what, 10, almost 11 years later. I presented on it saying that this works in the winery space. And you'll see that in just a minute. So what we're going to do again now is we still have our base, our water, our acid, and our rinse water. But now we're going to use potassium-based cleaning chemistries. So first off, you're going to, for your inorganic base, which actually you're using an inorganic base, hopefully most of you are, if you're doing this kind of acid water, or base acid rinsing, cleaning, you're probably already using an inorganic base. The problem is you're probably using sodium caustic. And the reason why you're using sodium caustic, it's cheap. It's cheap. However, going forward, at least in California, given our winery general order, we're being asked. I'm not exactly sure if we will, but we are being asked to reduce our sodium discharge. And so that would mean we would go to potassium hydroxide. No problem. No problem. Your folks, your cleaning supply people, they have potassium hydroxide. That's easy for them to get. It's going to cost you a little more, but that's easy. So the harder one is the inorganic acid for cleaning. And by the way, again, why do I want an inorganic acid? I don't want to have to digest it in my ponds later. I don't want to have to put more energy to digest this like I would citric acid. So the potassium-based acid is potassium bisulfate. I just want to be very, very clear. That's ATE at the end, not ITE. Not to be confused with SO2, not to be consumed with potassium metabisulfate. It's metabisulfite. This is potassium bisulfate. And you can see its structure right there. And this isn't a chemical new to you. You just may have never seen it. You may have never read the back of a cake box, your cake, your powder cake box. It adjusts pH in food. And actually, it's probably in some of your salad dressings as well. And this is food grade that we source, this potassium bisulfate. So it's nothing new to your world. It's just you may not have seen it before. The nice thing about this, and I'm going to point it out here and we'll talk more later about it, but I want to mention it right now because I've got both structures here. Notice that these are both monovalent. So 1+, 1+, the bisulfate is 1-. They're monovalent. And that's going to be key and critical for recapturing and reusing these chemicals. So but hold on to that note. The important part here for this slide, though, is that we remove the sodium. Sodium's gone, potassium's a little bit better for your soil than sodium. And that we got rid of the organic acids that we would have to digest in our ponds. So that's why we've chosen, Roger has chosen these two, this acid-base pair. Okay, so now we've got this selection. What happens if we just use it one time? Just one time. We're going to use it multiple times, but just what happens if we use it one time? So here's the chemistry. So you've got your base, your potassium hydroxide. Sorry, I'm trying to get my pointer to work here. You got your potassium hydroxide at 10 millimolar, and you've got your potassium bisulfate at 10 millimolar. That gives you these approximate pHs. That's just pH 2.2 is just maybe a little lower than your lemon juice. But here's the trick. When you go along, if you were to do it one time only, just like you're doing now, I think most of the industry probably just uses their chemistry once and tosses it down the drain. Hopefully, if you're a really good winery, you've maybe move it to a different tank and do it twice. But most of the time in the industry, we do it one time only. But if we were to do this, we want to mix these before we send them down to our wastewater pond. And if we do that, we get 5 millimolar potassium sulfate at pH 7. And that's really, really great. You want it at pH 7. No swings of pH in your ponds. Don't kill nematodes. Don't kill microbes. It's right where you want it. On top of that, it's not an organic acid, so there's no need for that oxygen demand. You're going to get it at about 5 millimolar, and that is just under 5 ppm potassium sulfate, not bisulfate, because you've now neutralized it, so it's potassium sulfate. If you go along and then combine that with your rinse water, because you also have a rinse water that you did in between, you're now going to be below you're going to be below 250 parts per million potassium sulfate, which is below the drinking water limits. So that's pretty amazing. I will tell you, I put this citation up there because if you look at how much sulfate is in grape juice, it ranges from about 30 parts per million to 2,200 parts per million. And we're going to be discharging, with the other rinse water, we're going to be discharging below 250 parts. So well below what most of your, in that range of where grape juice would have sulfate as well. So I just want to let you know, this is a good pairing. It's a good pairing. But again, we're not going to use it one time. We're not going to use it one time. We're going to use it multiple times. And how are we going to do that? We're going to do that with a nanofilter. And you can see that's a nanofilter right there. It's from VA Filtrations. You have one here up at the winery. You have one right here. It's used actually and for the winery's purposes for smoke remediation. But you can use it to clean up your cleaning chemistry. This is a tiny one, 10 gallons per hour. You go, oh, well, that's not a lot. If I have a big winery, I'm going to need to filter, forever. Well, you can filter all night long. This thing is small. Let it run slow. Let it run all night long. Size it to size it for your need, but size it small. So you're not just finishing up this in 1 hour and using a lot of electricity. Size it small so that it can run over 24 hours. The nice thing about the, again, oh, and by the way, a couple things about the nanofilter before I jump off. 100 to 300 molecular weight cutoff. So big things like proteins, polysaccharides, they're going to be discharged. They're not going to go through the filter. Your good clean stuff is going through your filter. As far as tartrate, that's going to be a divalent ion. It's going to be rejected. Your monovalents, as I mentioned before, your potassium, your hydroxide, your bisulfate is going to go through with the water, with the majority of your water, as you'll see in a minute. That's how you're going to recapture your cleaning chemistry and your water. Here's your basic wash. And you're going to, by the way, you're filtering these separate, by the way. Your two washes, you're going to keep them separate. Your basic wash is going to go through, your potassium's on one side, your hydroxide, and your water is going to go out as the permeate. And you can see below divalent ions, tartrate, proteins, polysaccharides, microbes. Of course, if you have microbes on the side of the tank, they're going to get kicked out. And the same with your acid rinse. You're going to have the same thing. Potassium's going through, bisulfate's going through. Ethanol, if it were around in the study, you're going to see in next, We had no ethanol around, our tanks were dry, but ethanol could slip through. If you were using a disinfectant like hydrogen peroxide, which I'm going to tell you more about later, that would go through as well. And that's okay. You want that cleaning chemistry too, or disinfectant if you had it. And again, remember, these are two separate streams that are filtered separately. Okay, here's the results. And this was some work by a student that I work with, Brooke Finale at UC Davis. She is a chemical engineer PhD candidate. So she's passed her QE. I've tried to highlight, back up. Sorry, giving away this punchline already. Just want to back up here. These are the highlights that are in yellow. First off, the base. You can see I've gone along and I've calculated the molarity before and afterwards based off of the pH. Based off of that, I get 35% recovery of the chemistry. Now that we would expect. If we've got tartrates on the side of our tank, that base is going to neutralize with those getting those tartrates off. So we actually lost a fair amount of the base. But what's pretty amazing is look at the water or the solution, the liquid. I got 96% back of the liquid. That's pretty amazing. Again, most of the time in the winery, what do? It's a one shot and it goes down the drain. So I'm getting back 96% of that liquid. As for the acid, here's the potassium bisulfate. I'm getting back a lot more of that chemistry. It's probably only going to be neutralized by any, water or any rinse water or any base that might have been left in the tank. But I get a majority of that back at 86%. And I still get 96% back of the liquid. You're probably going, how did I manage to get 96% back? Both of those seems pretty coincidental. Well, when you're doing this nanofilter and you've got 50 gallons and you've got it in a tub, you're basically just shrinking it down to a puddle where you're just about ready to, it's ready to run dry. So it was a physical limitation as to why we only got 96% back. We didn't get a lot of pressure buildup on the nanofilter. But I will tell you that what we did concentrate often had substance to it. Almost, there was one point where it looked kind of like egg whites, probably protein. And there was one instance where I walked away and Brooke looked at it and the thing turned white, almost milky white. So I'm talking to Roger, he thought that may have been polysaccharides in that case. But nonetheless, I'm concentrating up this, dirt, for lack of a better word, polysaccharides, proteins, microbes. But the clean stuff going through, I'm getting back some of my chemistry and a lot of my water. And that's really what the punchline is there. I'm getting 96% recovery of that water, which is about 20 times that water reuse. That was pretty unheard of, especially since all my life it's been a one shot and down the drain. So. Okay, now it's great to say we have these acids and these bases. It's whether or not they're effective. And I hope you would think that, yeah, they should be. I do acid and bases all the time in my winery. I mean, I've got caustic, sodium caustic, as opposed to potassium caustic, and I've got an acid. Should be effective. And yeah, it is. It is. So what I would suggest, by the way, this is the way we measured effectiveness at Behringer Winery. If you have an alternative method for your level and degree of cleanliness or sanitation, employ that. Test this for yourself. Don't take my word for this. Use your own method of determining effectiveness in your own winery. Well, here's what we did. So I'm showing you the results. This is a Firefly unit. So this measures ATP, relative light units. So ATP just tells you that there was biological life on the tank at some point. There may still be on the tank, it may or may not be, but there was some at some point. I hope you can see that we tested at 3 different spots: the door, the wall, the top. You can see the standard deviations are huge because we just went out to random tanks in our winery. And some were very dirty, some were actually fairly clean. Nonetheless, that's not the important part, because the important part was the after. The after was 0 across the board. And this was what we would expect with, again, a sodium caustic and a citric acid solution. So this didn't surprise us that we would not have any relative light units afterwards. So it's a different choice of acid and base. But this is what we would expect from the current one that we have as well. So we would expect the effectiveness to be very similar. So, okay.
And that was without a sanitizer?
No sanitizer. We'll talk about that at the end, and there is an opportunity for that at the end. If we want to go along and put it, well, when you say sanitizers, I meant disinfectant. If you want to put a disinfectant at the end, we'll talk about that, because that is another opportunity. And we have that ability. So preliminary cost analysis. I'm not so worried about potassium hydroxide. It is more expensive than sodium hydroxide. That's not the one that I'm worried about. I was worried more about the potassium sulfate. So that's what the preliminary cost analysis is at. So here you go. It's significantly more expensive. Potassium bisulfate was sourced from American Elements. I don't know if you know them. They're out of LA. As far as I know, that is United States state manufactured, produced, made in the US, sourced from the United States. Citric acid does come from Asia. It is significantly cheaper. And now realize this was a year and a half ago. So I don't know what this is today as far as tariffs and things of this nature. But nonetheless, we'll do apples and apples from a year and a half ago when I purchased this. You can see the rate concentrations are similar as pounds per thousand, but that's not that interesting. It's more about, it's interesting for the cost analysis, but the rate is about 10 millimolar potassium bisulfate, like we talked about. Citric acid is at 6.2, millimolar citric acid. That's just 1 pound per 100 gallons, which is what you normally tell your cellar people, just 1 pound per 100. You can see what the cost per cycle is. The cost per cycle is $11.32. And then the cost per cycle for the citric acid is $2.55. So for payback, I need to recycle that potassium bisulfate 4.4 times to have it just equivalent cost compared to citric acid. And if you ran the numbers in your head from the previous slide, you could probably figure out that it was going to be, because what I have is I have 96% solution. That means I need to put 4% of that solution back in to bring it up to the original volume. My raw chemistry recovery from that original slide was 86%, which means that kind of the net is about 83% of that chemistry recovery, which means I lost 17% of that. I can actually run this at 5.7 cycles, which means it works economically as well. Now, I would say you do need a nanofilter, but I also know that water is pretty valuable as well. And I know that I don't have to digest this in my ponds. So I've got an electrical savings too. So there's a lot more. I could do an additional analysis, but this is the preliminary cost. This is what my boss would want to see to say, hey, yeah, this works. Okay, so hopefully I'm still doing, how am I doing on time?
Close to time.
Okay, I'm almost close. Good, because I got one last thought, or two last thoughts. This is a possible skid recovery. I didn't want to leave you with, hey, get a nanofilter. No, this is kind of how it works. Filter your bases. But this is a very simplistic look here. You have your 3 tanks that would be your dirty solutions, your base, your acid, your water, rinse water. Because by the way, you're going to get your rinse water back too. And yeah, you'll get it back at 96% too. That's that physical amount you can't not get back. You'll put that through a nanofilter and it'll go to 3 tanks on the right-hand side, which would be your clean solutions. This doesn't have to be very complex though. I mean, we were using polytotes on some of these things. So it doesn't have to be very complex. It would be good if this was all automated so that you could go home at night and it would just automatically clean itself up, switch tanks, all that good stuff. So it would have nanofilter, you have your level sensors, you have your pH probes and your conductivity probes. It would tell you what you need to add in the morning. You'd add and then send it back out to your cellar. And by the way, the one thing about the cellar, the hardest part of all of this is not this skid. The hardest part with the cellar is just to remind them that it's sulfate and not sulfite. I'm just telling you right now, that's the hardest part. I've had to warn people a lot. Because the last thing you want to do is have a tank full of CO2, So the last part, and this is the part that ties to your question before about disinfectant. Hydrogen peroxide is a disinfectant. It's good for biofilm. And by the way, this unit from HP Now, you can see here, they originally approached me and they said, we use this in agriculture space with drip lines. They run this small amount of hydrogen peroxide through the drip lines to clean out the biofilm within the lines and the emitters. So it's an opportunity. But I want to use hydrogen peroxide. I just don't want to pull it in at 30% or 15% because I hope you all know it's a really strong oxidizer. It can get violent when it reacts. But this is an on-site generation in a machine. So it takes energy, water, about it, the air, and it can actually generate 1%. Now you can buy 3% in the bottles at the stores. This is 1%. You're thinking, well, that's not that much, 1%, that's pretty low. I can tell you that your working solution of peracetic acid has 700 ppm, so that would be 0.07%. So this is generating 1%. This is 10,000 as opposed to 700 parts per million. So I can actually, dilute 1 to 10 in my cleaning solution and still have more hydrogen peroxide than what peracetic acid has. So that's an opportunity for an additional disinfectant if you want it. And this is something, again, that Roger has pointed out in his paper here. He's provided some killing curves. It's worth looking at. It's worth looking at. So again, generated on site though. Don't haul around the concentrated stuff. So lastly, again, just want to thank the Ravenholt Lecture Series, Washington State, the Viticulture Enology Department, Brooke Finale, the student I work with, obviously Roger, and then of course this was done at the Behringer Winery.
No questions. Thank you very much, Bob.